Hello everyone and welcome back to Lattix training. Today we're going to look at working with dependency structure matrices in what is part 2 of this training. And we're going to learn how to read a DSM and derive information from that dependency structure matrix. We're going to learn the basics of working with DSMs. We're going to create a new project, extract data from our systems. We're going to look at something called member level analysis, which provides a more detailed view going to the smallest atomic elements in our system. Reading a DSM in detail and deriving insights from the dependency structure matrix. Reading the usage panes, configuring and filtering as well, creating new abstractions in the dependency structure matrix, and partitioning algorithms. So let's return to the ISO glib example that we looked at in part 1. We saw there that we have a C++ system, a library. It comes with its own architecture of those different layers. And in the dependency structure matrix, we can load and visualize the relationships between those layers. The first thing that you notice is that we have a matrix, an n by n square matrix of dependencies. And by way of reminder, we read across the row to see what a component is used by. So in this case, HAL, or the hardware abstraction layer, is used by driver 58 times. And if you scroll over to the navigation panes over on this side, you can see in more detail what those dependencies are. In this case, they consist of type references, includes, data usages between those components with a strength of 58. So there are 58 usages of the hardware abstraction layer by driver. And similarly, there are 7 usages of HAL, the hardware abstraction layer, from scheduler. So here you see the relationships between key parts of our systems. Reading across the row, we see what a component is used by, but reading down the column, we see what a component is using. So here, driver is using util, driver is using HAL 58 times, and it's using this global group of unstructured elements called star 4 times. So here, this is how we read a DSM. Across the row is used by, down the column is what a component is using. Now you'll notice that COM is sitting at the top of this architecture. We have already applied something called partitioning, but let's look at partitioning algorithms now. So if I select the core component, or the matrix here of the matrix, the high-level component, that will select the whole dependency structure matrix, and we can click the down arrow, and we have at our disposal various partitioning algorithms. By default, when you load a system in Lattix, it's often alphabetically ordered. So for example, you might see when you load this project for the first time that COM is at the top, driver, HAL, scheduler, and util, and it's following an alphabetical ordering. However, in software systems, that's not the most natural way of organizing the system. We want to organize by usage. We want to group by usage. And that's what these partitioning algorithms are designed to do. So for example, if I select component partitioning, that will group by component usage. There are other algorithms such as provider proximity, reachability, spectral, as early as possible, as late as possible, alphabetical, as we've seen, naming, and disjoint. For most software systems that we consider, component partitioning is the one that we would normally choose. And if you select this ... at the bottom, you can apply your partitioning algorithm recursively. That will then go through all the subsystems and also partition those by the same algorithm. So I'm going to use component partitioning. I'm going to select this here, and you can see now it's ordering by a different algorithm. It's put COM at the top, which reflects our architecture diagram as well. And you can see the percentages here. The percentages are the amount of the system contained within that component. So COM, you can see, is carrying 81% of the entire system here, whereas util comprises only 2%. This is actually quite useful information right off the bat, for example, for prioritization of development resources or testing resources. We kind of get a sense of how distributed the load is across these different components. Because we've applied partitioning recursively, if I open up COM, this will already be partitioned. And we can see in this case, network management here has gone to the bottom, and data link has also gone to the bottom. Those were part of our core mandatory modules in the architecture diagram, if you remember. And you can see then these optional modules that we set rules for at the end of the first part of the training. They sit above data link and network management. Mostly they are independent of each other as desired by the design. However, we've seen that there are some couplings between, for example, task controller and virtual terminal client that violate that software architecture diagram we first considered. We also see things like this, where you have a component that's heavily used. If you remember, the rows are used by and the columns using. This particular component is used by lots of things and is using lots of things above and below. So this is what we call a change propagator. In fact, if I was to mark this component as changed, which I can do even at this high level, then I can run an impact report. And what we would see that an impact report on the changed tag here that we've just applied to this network management component, you would actually see that running the impact report on a change to this component shows us that changing that component has 8 levels of impact. So this really ripples through the system, and a fifth of the system would be affected by a change to that component. So already we're getting a sense of the importance of that component in this architecture. And we actually see that this is level 1 of impact. All of these subsystems are used by all of these subsystems, all of these subsystems used by all of these subsystems, and so on until you get to the outermost level of impact, where you have the complete transitive closure of a change to that network component. So this is really useful data so that you can assess the impact of a change to your system. Obviously, that's something we want to minimize. Generally, we're trying to minimize the cost of change. And if we change a component, we don't want it to ripple and cause unnecessary effects or retesting or recertifying efforts. That's why modularity is so important. If we can modularize, keep our components isolated, functionally separate where possible, then this is a good thing, because the ripple of a change is then minimized, and that's what we want. So that's how to read a dependency structure matrix by usage and by rows and columns, and also these information panels on the side here. You can see the information panel, which gives us the data on what we're seeing in the dependency structure matrix. We also have the usage panel where we can select any cell and, for example, see this usage from driver to scheduler. So this is a usage from this particular include file in schedulerc.h up to canioc.cbp, which is using that particular file. And so driver is using scheduler. Scheduler is also using driver in a stronger sense, 19 dependencies. You can see those dependencies here. All of these things used by on these usages here. So really easy to see where things are being used. And of course, you can drill down into the dependency structure matrix to see the breakdown of those 19 relationships. 6 of them are to the CAN and 13 to the system component. Again, you can break down and see exactly where those relationships are to the scheduler, even down to the method level. So for example, if we wanted to see more detail about these 2 dependencies, you can actually see the methods that are used here, and you can expand to the member level. And if we expand to the member level, we actually see the individual methods that are called that actually have those dependencies up to scheduler. So really easy to see what a component is used by and what a component uses in the other direction, and see the unwanted coupling as well. Okay, so that concludes this introduction to looking at a dependency structure matrix and working with a DSM. Thank you very much.